Dear students, next topic is limit point or cluster point. A real number L is said to be a limit point or a cluster point of a sequence if every neighborhood of L contains an infinite number of terms of the given sequence. Thus, L is a limit point of sequence an if for given epsilon greater than 0, an belongs to L minus epsilon to L plus epsilon for infinitely many values of n. Second definition, a real number L is said to be a cluster point or limit point of a sequence an if given any epsilon greater than 0, however small, and a positive integer m, there exists a positive integer k greater than m such that ak minus L mode value will be less than epsilon, that is, ak is between L minus epsilon to L plus epsilon. This definition states that after first m terms of the sequence, a term ak of the sequence can always be found such that ak minus L mode value is less than epsilon. Epsilon is greater than 0, however small any arbitrary number. This means after any number of terms of the sequence, there is always at least one term of the sequence which lies in the interval L minus epsilon to L plus epsilon. Since epsilon can take any value, L minus epsilon to L plus epsilon is an arbitrary neighborhood of L. Remarks: a real number L is not a limit point of a sequence an if there exists at least one neighborhood of L which contains only finite number of elements of an. Second, difference between limit of a sequence and limit point of a sequence. Real number L is limit of sequence an if every neighborhood of L contains all the terms of the sequence except the first finite number of terms a1, a2, am minus 1. Real number L is a limit point or a cluster point of sequence an if every neighborhood of L contains infinitely many terms of the sequence and infinite number of terms of the sequence may lie outside this neighborhood. Thus, limit of sequence is limit point of the sequence, but limit point of a sequence may not be the limit of a sequence. Number third, every limit of sequence an is also a limit point of the sequence an, but converse is not true. For example, the sequence 0, 1, 2, 0, 1, 2 has 0, 1, 2 as its limit points, but limit of the sequence does not exist. Number 4, if the values of only a finite number of terms are same, then the limit points of the sequence and the range set an such that n belongs to n are same. This means that the limit points of a sequence an are either the points or the limit points of the range set. Making illustrations of these definitions, the sequence minus 1 raised to power n is equal to minus 1, 1, minus 1, 1, minus 1, 1 has two limit points, minus 1 and 1, but limit of sequence does not exist. The sequence 1 plus minus 1 raised to power n is equal to 0, 2, 0, 2 has two limit points 0 and 2, but limit of sequence does not exist. Each of the sequence 1 by n, 1 by n cube, 1 by 3n minus 1 by n square has only 0 as its limit point. None of the sequence n square, n minus n cube has a limit point. Next theorem, if limit when n tends to infinity an is equal to L, then L is the unique limit point of sequence an. Or we can restate, convergent sequence has a unique limit point. Proof, here limit when n tends to infinity of an is equal to L, therefore for any epsilon greater than 0, there exists a positive integer m such that an minus L mode value is less than epsilon for all n greater than equal to m. This implies an is between L minus epsilon to L plus epsilon for all n greater than equal to m. This implies L minus epsilon to L plus epsilon contains infinitely many terms of an. Thus, every neighborhood of L contains infinitely many terms of the sequence an. Hence, L is the limit point or cluster point of the sequence. Uniqueness: suppose that L dash is any other limit point of an. As an converges to L, therefore, for every epsilon greater than 0, there exists a positive integer m such that an minus L mod value will be less than epsilon by 2 for all n greater than equal to m, marking this to be number 1. As L dash is limit point of an, therefore for every epsilon greater than 0, there exists a positive integer k greater than m such that an minus L dash mod value will be less than epsilon by 2 for all n greater than equal to k, marking this as number 2. Now from first and second, an minus L mod value is less than epsilon by 2 and an minus L dash mod value less than epsilon by 2 for all n greater than equal to k. Now if we consider this term L minus L dash mod is equal to L minus an plus an minus L dash mod value, adding an and subtracting an, and using the identity an minus L plus an minus L dash value will be greater, and this is becomes less than by epsilon. As epsilon is arbitrarily small and L minus L dash mod value is less than epsilon, so taking this value to be 0 or this is equal, L is equal to L dash. Hence, L is the unique limit point of sequence an. Now, making remark, converse of the above theorem need not be true. For example, consider the sequence an where an is equal to n if n is odd, 1 by n if n is even. Here 0 is the only limit point, but the sequence is not convergent. A sequence may or may not have a limit point. The sufficient condition for the existence of a limit point of a sequence is given in the following theorems. Next result is called Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. Every bounded sequence has a limit point, or every bounded sequence has a cluster point. For the proof, let an be a bounded sequence. Therefore, the range set S of the sequence is bounded, where S is equal to an such that n belongs to n. Case first, when set S is finite. In this case, there exists at least one member of S, say L, such that an equal to L for infinitely many values of n. Therefore, for each epsilon greater than 0, the open interval L minus epsilon to L plus epsilon contains infinitely many terms an equal to L of the sequence an. Hence, L is a limit point of sequence an. Now, case second, when set S is infinite. In this case, the set S is an infinite bounded set. Therefore, by Bolzano-Weierstrass theorem, for sets, the set S has a limit, say L. Thus, the neighborhood of L contains infinitely many elements of set S. That is, neighborhood of L contains infinitely many terms of sequence an. Hence, L is a limit point of the sequence an. Now, taking corollary, if S is a compact set, that is closed and bounded, then every sequence in S has a limit point in S. For the proof, let an be a sequence in S, that is an belongs to S for all n. Now, sequence an is bounded. Since S is bounded, therefore an has a limit point LC by theorem 2.23. We shall now prove that L belongs to S. L belongs to, if L belongs to S complement, where S complement is open and it is a neighborhood of L and contains no terms of the sequence an. This is a contradiction to the fact that L is a limit point of an. Therefore, L does not belongs to S complement. This implies L belongs to S. Remark: an unbounded sequence may or may not have a limit point. Sequence n square equal to 1, 4, 9, 16 is an unbounded sequence having no limit point. Sequence 1, 2, 1, 4, 1, 6 is an unbounded sequence having 1 as its limit point. Now, taking example, give an example of a bounded sequence having two limit points. This is example minus 1 raised to power n. An is equal to minus 1, 1, minus 1, 1, minus 1. The sequence an has two limit points, minus 1 and 1. Second, give an example of a bounded sequence having three limit points. For this, suppose we have a sequence having elements as 1, 3, 5, 1, 3, 5, 1, 3, 5. The sequence has three limit points. Now the next result, the set of limit points of a bounded sequence is also bounded. For the proof, let an be a bounded sequence. Then there exist two real numbers k and k such that an is between small k to capital K for all n belongs to n. Let L be any real number. Now, if L belongs to k2 minus infinity, then k2 minus infinity is a neighborhood of L and contains no elements of an. Therefore, L is not a limit point of an. Likewise, if L belongs to k2 infinity, then k2 infinity is neighborhood of L and contains no elements of an. Therefore, L is not a limit point of an. Therefore, no point outside k to k is a limit point of an. Thus, all the limit points of an lie in k to k. Hence, the set of all the limit points of the sequence an is bounded. Making remark, the set of limit points of an unbounded sequence may or may not be bounded. For example, consider the sequence 1 plus 1 by 2, 2 plus 1 by 2, 1 plus 1 by 3, 2 plus 1 by 3 and so on. The above sequence is unbounded and set of its limit points is set n, which is unbounded. Again consider the sequence 0, 1, 0, 2, 0, 3, 0, 4 so on. The above sequence is unbounded and the set of its limit points is singleton 0, which is bounded. Now, next definition for Cauchy sequences. A sequence an is said to be a Cauchy sequence if for given epsilon greater than 0, there exists a positive integer m such that an minus am mode value will be less than epsilon for all n greater than equal to m. Second definition, a sequence an is said to be Cauchy sequence if for given epsilon greater than 0, there exists a positive integer m such that am plus p minus am mode value is less than epsilon for all p belongs to n. For example, consider the sequence an is equal to an in which terms a20 is equal to 1 by 20, a21 is 1 by 21, a22 is 1 by 22. Therefore, the term a21 minus a22 giving value as 1 by 420. Similarly, second a22 minus a20 is 2 by 40, 440. A23 minus A20 is giving as value 3 by 460 and A100 minus A20 is giving value as 1 by 25. Similarly, continuing, A1000 minus A20 is equal to 49 by 1000. Thus, we see that An minus Am mode value becomes less than 1 by 20 for all n greater than equal to m, where m is equal to 20. Therefore, sequence an is a Cauchy sequence. Now, remark, A sequence an is a Cauchy sequence if for given epsilon greater than 0 we can find a term am of the sequence such that the difference between any two terms of the sequence after this term is less than epsilon. Making illustration, the sequence an equal to 1, 1 by 2, 1 by 3, so on 1 by n is a Cauchy sequence. Let epsilon greater than 0 be given number. For all n greater than equal to m, we have an minus am mode value is becomes equal to n minus m divided by nm, and we can write this is value is less than by n minus m, that is 1 by m, or an minus am is less than epsilon if 1 by m is less than epsilon, or an minus am mode value is less than epsilon if m is greater than 1 by epsilon. Thus, we can find positive integer m which is greater than 1 by epsilon such that an minus am mode value is less than epsilon for all n greater than equal to m. Therefore, an sequence is a Cauchy sequence. Illustration second, the sequence n square is not a Cauchy sequence. Here an is equal to n square. Let epsilon greater than 0 be any given number. Therefore, an minus am is equal to n square minus m square, writing as n square minus m square, and this value is greater than 1 for all n m belongs to n and n is greater than m. This implies an minus am mode value is greater than 1 for all n m belongs to n and n is greater than m. If we take epsilon is equal to 1 by 2, we see that an minus am mode value is greater than epsilon for all n m belongs to n and n is greater than m. Hence, an is not a Cauchy sequence. Now, third one. Illustration third, the sequence an is equal to minus 1 raised to power n is minus 1, 1, minus 1, 1, minus 1 is not a Cauchy sequence. Here am plus 1 minus am is equal to giving value as 2. If we choose epsilon equal to 1 by 2 be a given number, therefore am plus 1 minus am mode is greater than epsilon for all m belongs to n. This implies an is not a Cauchy sequence. Show that the following sequences whose nth terms are given below are Cauchy sequences. Here an is given as 1 by n square. Let epsilon greater than 0 be any given number. For all n greater than equal to m, we have an minus am is equal to 1 by n square minus 1 by m square is equal to 1 by m square minus 1 by n square, since 1 by n square is less than by 1 by m square. Therefore, we can say that an minus m is less than 1 by m square, or an minus am less than epsilon if 1 by m square is less than epsilon, or an minus am mode value is less than epsilon if m square is greater than 1 by epsilon, or an minus am mode is less than epsilon if m is greater than 1 by square root of epsilon. Let m be any positive integer greater than 1 by square root epsilon, then an minus am mode is less than epsilon for all n greater than equal to m. Hence, an is a Cauchy sequence. Try second part. Example second, prove that every Cauchy sequence is bounded. Is the converse true? If not, show by an example. Let epsilon greater than 0 be given number and an be any sequence which is Cauchy sequence. Therefore, there exists a positive integer m such that an minus am mode value is less than epsilon for all n greater than equal to m, or we can say that an is between am minus epsilon to am plus epsilon for all n greater than equal to m. Now let k1 is equal to minimum of a1, a2, am minus 1, am minus epsilon, and capital K2 equal to maximum of a1 a2 am minus 1 and am plus epsilon. Therefore every term of the sequence an is between k1 and k2. Therefore an is between k1 and k2 for all n belongs to n. Hence sequence an is a bounded sequence. Now converse of the above theorem is not true. Consider the sequence an where an is equal to minus 1 raised to power n. Since an is bounded minus 1 and 1, since an is bounded sequence but not a Cauchy sequence as proved in illustration third above. Now next result is Cauchy's general principle of convergence. A, a sequence converges if and only if it is a Cauchy sequence. This is the general principle given by Cauchy. Case first, or here it is given that an is convergent to L. We shall prove that here an is a Cauchy sequence. Since an converges to L, therefore using here definition for convergence, therefore for given epsilon greater than 0, there exists a positive integer m such that an minus L mod is less than epsilon by 2 for all n greater than equal to m, marking this to be number 1. Or for the particular m, am minus L is less than epsilon by 2, marking this to be number 2. Now consider an minus am mod, or we can write this as less than equal to an minus L plus L minus am, or using above 1 and 2 here this becomes less than epsilon. An minus m is less than epsilon for all n greater than equal to m. Hence an is a Cauchy sequence. Now the converse part. Here it is given that an is a Cauchy sequence. We shall prove here an is convergent. Since an is a Cauchy sequence, therefore for given epsilon greater than 0, there exists a positive integer m such that an minus am mod value is less than epsilon by 3 for all n greater than equal to m, marking this to be number 1. Also, every Cauchy sequence is a bounded sequence. Therefore, using the condition for boundedness. Therefore, an is bounded, but every bounded sequence has a limit point LC. Therefore, there exists a positive integer k greater than m such that ak minus L mod is less than epsilon by 3, marking this to be number 2. Also, first becomes ak minus am mod is less than epsilon by 3, marking this to be number 3. Now the consider an minus L and writing this identity less than by this identity an minus am mod plus am minus ak mod plus ak minus L, and using 1, 2 and 3 here becomes therefore an minus L is less than epsilon for all n greater than equal to m. Hence the sequence an converges to L. Making remark, Cauchy's general principle of convergence can also be stated in the following forms. A sequence an converges if and only if for each epsilon greater than 0, there exists a positive integer m such that an minus am mod value is less than epsilon for all n greater than equal to m. That is am plus 1, am plus 2 plus so on an mod is less than epsilon for all n greater than equal to m. Or second, we are restate a necessary and sufficient condition for the convergence of a sequence an is that for each epsilon greater than 0 there exists a positive integer m such that an plus p minus an mod value is less than epsilon for all n greater than equal to m and p is greater than equal to 1. Now for the proof, condition is necessary. It is given that an is convergent. Therefore, for a given epsilon greater than 0, there exists a positive integer m such that an minus am is less than epsilon by 2 for all n greater than equal to m. Now, if we consider this term an plus p minus an, this is equal to an plus p minus am minus an, or we can write this is less than by this identity an plus p minus am mod plus an minus am mod, and using 1 here, this is less than epsilon by 2 for all n greater than equal to m and p is greater than equal to 1. Therefore an plus p minus an is less than epsilon for all n greater than equal to m and p is greater than equal to 1. Now condition is sufficient. It is given that an plus p minus an mod is less than epsilon for all n greater than equal to m and p is greater than equal to 1. Taking particularly n is equal to p, we get am plus p minus am mod is less than epsilon where p is greater than equal to 1, or ak minus am is less than epsilon for all k greater than equal to m. Thus an is a Cauchy sequent and hence convergent. Now taking next example, use Cauchy general principle of convergence to show that sequence n by n plus 1 is convergent. Now solution, let epsilon greater than 0 be any given number and an is equal to n by n plus 1. For all n greater than equal to m, we have an minus am. After solving, we have n minus m divided by n plus 1 m plus 1 mod value, and this can be shown as less than by this quantity, that is 1 by m. Therefore an minus am mod value is becomes less than 1 by m, or an minus am mod value is becomes less than epsilon if 1 by m is less than by epsilon, or we can say an minus am mod is less than epsilon if m is greater than 1 by epsilon. Therefore let m be a positive integer greater than 1 by epsilon, then an minus am mod value is becomes less than epsilon for all n greater than equal to m. This implies an is a Cauchy sequence, but every Cauchy sequence is convergent, therefore an is convergent. Now fourth example, show that sequence an defined by an is equal to 1 plus 1 by 3 plus 1 by 5 plus so on 1 by 2n minus 1 does not converge. Now solution is, let epsilon greater than 0 be given number. Here am is equal to 1 plus 1 by 3 plus 1 by 5 plus so on 1 by 2 m minus 1, and a to m term is writing term by, therefore consider a to m minus am we have solution is, that is this can be written after solving, can be written as less than 1 by 4. Therefore a to m minus am is becomes greater than 1 by 4. If we take 1 by 4 as epsilon, we have a to m minus am mod is becomes greater than epsilon for all m belongs to n. This implies an is not a Cauchy sequence and hence not convergent. Now example fifth, show that the sequence an where an is equal to 1 plus 1 by 5 plus 1 by 9 plus so on 1 by 4 n minus 3 does not converge, while bn defined as bn is equal to 1 by n, an converges to 0. Now for solution, am is given as this term, a to m writing a, therefore a to m minus am is this, and this can be made less than by 1 by 2m plus 1 by 8m plus so on 1 by 8m, and that is 1 by 8. Therefore mod of a to m minus am is greater than 1 by 8 for all m belongs to n. Let epsilon greater than 0 be any given number. Taking epsilon is equal to 1 by 8, we get a to m minus am is greater than epsilon for all m belongs to n. An is not a Cauchy sequence, but bn is 1 by n an, therefore bn is this one, if we suppose that let Tn is equal to 1 by 4 or n minus 3, its limiting value is 0. Therefore by Cauchy first theorem on limits, limit 1 by n into t1 plus t2 plus tn will be equal to 0, and therefore limiting value of bn is 0. Hence 1 by n an bn an converges to 0. Okay dear students, try exercise 2.4. If you have any problem then discuss with me. Thank you.